In this video, we're going to talk about how to calculate torque. So once we did in Unit 1, we did kinematics. Unit 2, we did forces and dynamics. We did F net equals ma. We're going to do a very similar thing here. We're going to use the net torque equals I alpha, which is what causes angular acceleration. So the first step is to figure out how do we calculate the equivalent of force in rotation, which is torque. So the second part of, after we did kinematics, we did forces and dynamics. And so now we're going to talk about a similar thing, a dynamics when it comes to rotating, right? So in linear motion, forces cause the change in velocity, cause an acceleration, right? And so something has to cause an angular acceleration, and that is the thing we call it is torque. Okay, so it still requires a force. Torque is what causes a change in the angular velocity. So let's say I have something like this and I want to rotate it. Okay, I want to cause it to rotate here. And I want you to think of there's a few things that will factor into it. Again, whenever you want to cause a change in the motion of an object, it requires a force. So torque is related to force, but there's some things you have to keep in mind. So this is our axis of rotation where I'm pinching it here. And so this is, I want to cause this thing to rotate here. So I can apply my finger and I can push it. So if I rotated this, push upwards, it would cause it to rotate that way. If I push downward, it would cause it to rotate the other direction here. Now, here's the thing that's interesting, right? So it matters the direction of the force, right? The direction of the force is going to impact the direction of the rotation. And also keep in mind that there has to be some kind of perpendicularity, because if I push on the end this way, it doesn't cause it to rotate, only when I'm doing it this way or this way. So the direction of the force impacts it, and it's direction relative to something, and we'll talk about that something here in a little bit. The other thing is also the same amount of force. If I do it here closer to the axis of rotation, it doesn't rotate quite as much. It's easier to rotate it when I do it further away from the axis of rotation. So the position of where the force is located also matters, and the direction of the force matters. And those are the two main things that kind of factor into the calculation of what's going on here. Now, in general, we're going to have a similar thing to what we call F net equals ma. This is our Newton's second law of motion. So the left side, this is going to be net torque. So you can see the angular acceleration is related to the linear acceleration. But we have two other values here. We call this the net torque, and we use the Greek letter. This is the Greek letter tau. Tau is the Greek letter for this. We use for torque. And then this other term called I is called rotational inertia. We'll talk about this one in another lesson. For now, we're just like we did F net equals ma, right? That was our next step, is to figure out how do we draw that free body diagram, calculate the forces. We're going to focus on the net torque. Now, a couple things you have to keep in mind when we're doing this. Because it matters where the force is going, it's going to change how we draw our free body diagram slightly. But let's first talk about how do we calculate the torque at its mechanics. So torque is this R times F perpendicular, or rFsinθ. I tend not to use this one. I rather you think about these. So let's understand this R vector. Sometimes this is called the line of action. There's various terms for this. I call it R vector. I think it's the most simple thing. It is simply a vector pointing from the axis of rotation to where the force is applied. So when we were doing the pen here and I'm applying a force on the end, the R vector is literally a distance vector from the axis of rotation to where that force was being applied. Okay, we always draw it as part of when we're calculating it. And what we want to do is, rather, like kind of when we did work and energy, we multiplied the parallel components. Like if we did force and the displacement, or if the force was like when we did, just revisiting on work, when we did the force vector and then the displacement was this direction, remember we decomposed it and we only multiplied the force parallel component. In this case, when we do the torque calculation, we want the perpendicular components to them. So for example, if I have an R vector that points this way and I have a force vector that points this way, I don't care about the component of the R parallel to the force. I care about the component that is perpendicular to the force, and that's because when we were causing this rotation, there has to be kind of like at a right angle to something. And it was not right angle to the pen necessarily, but this R vector. So this is the R like parallel, or this is the R perpendicular. This is the component perpendicular. This is the parallel. We care about the perpendicular component. Now we can either decompose the R or the force vector when we calculate this torque. And let's go through some examples. Keep in mind, torque is still a vector quantity, so we still do the clockwise, counterclockwise direction there. Okay, so let's go through an example here. Let's say we're rotating around the axis of rotation. This is our axis of rotation right here. We'll just put it right here. Our axis of rotation, this is our axis. And we want to calculate the various r vectors, and we want to, assuming this is the axis of rotation, we are given these blue vectors. These are r vectors, and then our red vectors are force vectors. And this will matter because when we draw a free body diagram, we're going to do this. But for now, let's just go through the mechanics of the computation. So we have our r vectors are in blue, the force vectors in red. Let's go through all the torques. Now let's assign a direction. We'll say counterclockwise is the positive direction, and therefore clockwise is the negative direction. For every torque, you got to think, is it causing it to rotate clockwise or counterclockwise? So let's look at F1 here. The r vector is 3 meters. It's already perpendicular to F1. So when we do the torque around 1 here, you're just going to do this 3 times F1. They're already at a right angle, so you just multiply them straight up. Okay, and the F1, and now is it a positive or negative torque? Well, if I were to pull on this object or r vector this way, it would cause it to rotate clockwise, right? I'm pulling it. Think of it this way. I'm pulling it down this way because it's rotate clockwise. So that makes it a negative torque there. Let's look at F2. F2, the r vector is pointing up, and the F2 vector is this way, but we got to decompose it because they're not at right angles yet. So we want to make our right triangle decomposition. This is F2 sine 30 degrees. This is F2 cosine 30 degrees. Got to be good at that vector decomposition. And we want the component perpendicular to the r vector here. Okay, now this, if I pull to the left here from this vertical thing, it would rotate it counterclockwise. So that's a positive torque. So it'll be positive F2 cosine 30 degrees times 2 meters there, times 2. Okay, and oh, that would be the torque from 2, F2. Sorry, we'll call it torque 2. Okay, how about force 3? Well, it's acting at the axis of rotation, so the r vector is 0. So torque from 3 is going to be 0 because the r is 0. There is no vector from the axis of rotation. Whenever you're acting at a force at the axis of rotation, it won't cause it to rotate. And you can see it here when we're rotating around our thumb point. If I just put a force right here on it, it's not going to cause it to rotate at all. So there's no torque there. Here for torque 4, we have the r vector pointed to the right, but the force vector is not perpendicular, so we have to decompose it into 2 components. This is 20 degrees, so this is F4 cosine 20 degrees. This is F4 sine 20 degrees. So then what do we care about is we care about the component perpendicular to that r vector. So we would multiply the F4 cosine 20 degrees times the 2 meter here, which is at a right angle, and then so those are already perpendicular. And then, is it positive or negative? Well, if I pull down on the thing over here, it would cause the whole thing to rotate clockwise, which is the negative direction. So that is a negative torque there. Okay, so that's the mechanics of how we do that r vector, right? You got to draw that r vector. We got to do the perpendicular component there. And in this case, we always decompose the force vector. Now, you might be like, Alan, the formula up here you told me had a sine theta. What's the deal here? Well, the tricky thing about the sine theta, and the reason I don't use it, and I want you to think of as perpendicular, because the sine theta refers to the angle between the 2 vectors. The angle you're given is not necessarily the angle between the 2 vectors. Like, for example here, we have a vector here and here. This is 30 degrees. But technically, the angle between the 2 vectors is this angle right here. That's the angle that's made between the two vectors. And that one is not 30 degrees. Actually, complementary, it's 60 degrees. Okay, so that's why we use cosine here, because the angle was not the angle between the 2 vectors. If you want to use the sine theta, you got to remember that theta has to be the angle between the 2 vectors, and you can't use any other angle for that, which is why I tend not to do that. I tend to just make sure, hey, it is the component that's perpendicular to that vector. That's how we calculate the torque. Okay, let's go through one where we might have a free body diagram. Assume that the potential is 50 newtons, compute the torque around the axis O. So here's our axis of rotation right here. And the r vector is not shown in this problem. We have to draw the r vector. The r vector is a vector from the axes pointing to where the force is applied. So this is 6 meters right here. That's my r vector right there. Now, it's not perpendicular to the torque, so we have to decompose, or the tension. We need to decompose the tension into T cosine 30 degrees and T sine 30 degrees, right? And then to calculate the torque, I'm going to do the R vector times the perpendicular component of the force. So that's going to be 6 times T sine 30 degrees. Now, is it positive or negative? Depends on our direction. Let's say this direction is positive and clockwise is negative again. If I were to lift up on the bridge, it would cause it to rotate counterclockwise. So that makes it a positive torque by my definition. And so then this would be 6 times 50, because they told you the tension is 50, times sine of 30 degrees. Sine of 30 degrees is 1/2, so this is going to be 150. Units of torque are Newton times meters, because remember the torque is R times F. This is measured in meters. This is measured in newtons. So they call them Newton meters. There's no special name for the torque units. If you found this video helpful, come check out our school community. It's got an amazing bunch of features. It's got extra videos, corrected videos, better than the ones that I have errors on YouTube. It's got multiple choice free response questions. I hold live Q&A sessions and go through more problems and I answer students' questions, help with schoolwork, all kinds of things. If you want to check it out, look in the description below or check out the website and find us in the school community. You get a 7-day free trial to give it a shot, just to check it out, see what it's like, come join some calls, and honestly, come learn AP Physics 1 even faster with us.